Right now, I'm going to introduce you to discrete least squares. In engineering, there are many situations where we need to understand the relationship between two variables by doing experiments. Sometimes there is no existing theory to describe this relationship with a formula. So how are we going to analyze the data? We use the curve fitting, least square, or interpolation. So the curve fitting is a process of finding equations that best match the collected from experiments. There are two main methods using in curve fitting. First is least squares methods, which is used when the data has some error, and interpolation method, used when the data is assumed to be exact with no error. Right now, I'm going to introduce you to fitting a line linear regression. The goal of the linear line squares method is to find a straight line that best fits a data set to the data points. This best fit line is the one that makes the total error as small as possible. The error is measured by adding up the squares of the differences between the actual data points and the values predicted by the line. So the steps of fitting a line is write the linear function to be fitted, find the normal equation in the matrix form 2 by 2, find the values for all the equations of the matrix, n to the n of the data points, as in the equation. So for a0 and a1, thus the least square line is fx equals to a0 plus a1x. Next is fitting a polynomial degree 2 or more. So fitting a polynomial degree 2 or more, or a polynomial regression, involves finding a polynomial equation that best approximates the relationship between a dependent variable and one or more independent variables. This is useful when the relationship between the two variables isn't linear and might involve curves, turns, or other nonlinear patterns. Steps for fitting a polynomial of degree m. Determine the degree m of the polynomial and write the general expression of the polynomial. Degree equals to m, fx equals to a0 plus a1x plus a2x squared plus etc. plus am xm. Write the normal equation in matrix form n plus 1 x cross product m plus 1. Find the values for all the elements of the matrix, n which is the total number of data points, and the rest of elements. So for the coefficients a0, a1, etc. am, thus the least square function is fx equals to a0 plus a1x plus a2x squared plus a etc. amx to the power of m. As you can see at the table, you have the 6 functions, the main functions, which is the function of y equals to ax squared plus b, 1 over y equals to ax squared plus b, y equals to a b to the power of x, ln y equals to ln a plus x ln b, y equals to ax b, ln y equals to ln a plus b ln x. And the list goes on until the list number 6. So how we are going to fit a transcendental function? First, we're going to identify the expected function, fx, or the model. Identify the unknowns, linearize the relationship of the independent and the dependent variables, transform the data, identify the normal equations, determine all the respective values, solve for the coefficients, solve for the unknowns, write the model obtained by the data.
The main purpose of this assignment was to learn how to apply curve fitting to experimental data. It involved using both linear and polynomial regression to model relationship in the data. One important goal was to compare interpolation method with least squares fitting, especially in terms of accuracy. Another focus was learning how to turn non-linear models into linear ones using data transformation technique. Throughout the process, different polynomial degrees were analyzed to understand the risk of overfitting or underfitting. Visual tools such as graph were used to help assess how well each model fits the data. Lastly, these tasks provided experience in using software like Microsoft Excel and Python for running regression and transforming data. The assignment started by examining the data to see how the x and y variables were related. A scatter plot was used to visually check if the pattern was more linear, curved, or exponential. For linear trends, a straight line model was fitted using the least squares method. For curved trend, polynomial models like quadratic were used to better follow the shape of the data. In cases where exact prediction between points were needed, interpolation methods would apply. When the data looked non-linear, transformations such as logarithm were used to make the data fit a straight line, which made it easier to analyze. Each model was checked for accuracy by using plots and error value. Polynomial degrees were compared to find a good balance between complexity and accuracy. Python was used to help manage the data, run the model, and plot the result. Libraries like NumPy and Pandas helped in handling the data, while Matplotlib was used to draw graph. For fitting the data, functions like polyfit from NumPy were used for linear and polynomial model. For interpolation, the SkyP library provided tools to estimate values between points. To turn exponential or logarithmic trends into linear ones, Python made it easy to apply transformation. Residual and error values were also calculated using Python, which helped evaluate the models. Overall, Python made the whole process faster and easier by automating the step and allowing experiment with different models.
The analysis was implemented in Python using several key functions. We use np.polyfit bracket open bracket close to calculate the best fit coefficients for linear and quadratic models, and np.poly 1d bracket open bracket close to generate functions from those coefficients for easy prediction and plotting. For the exponential model, we first transform the data using np.log open bracket close bracket to linearize it, and we apply np.polyfit close bracket open bracket close bracket on the transform data. And then we use np.exp open bracket close bracket to revert it back to the exponential form. So the resultant exponential model was y equals to 0.888 times the ASP 0.0088 x. So for the interpolation, we use inter p1d open close bracket from psi pi to estimate values between known points. So for matplotlib is scatter and plot. They were used to visualize all three models alongside the actual data. We also defined a custom function to compute the SSE, where comparing each model's prediction with the actual temperature anomalies. The result clearly shows that the quadratic regression model provides the most accurate fit, validating it as the most choice for modeling this dataset. Overall, Python made the entire process efficient, flexible, and easy to visualize. As you can see for the results of the data we get from the Python,
in the first part of the assignment, the regression line was calculated manually using the method taught in class. The goal was to find the best straight line that fits the data points. To do this, the value of the slope and y-intercept were calculated step by step. This involved using the totals of all x values, y values, the product of x and y, and the squares of x value. Once the slope and intercept were found, they were used to form the equation of the line. Then, using this equation, predicted values were calculated for each x value. The difference between each actual y value and predicted value was then found, and this difference was squared. All the squared differences were added together to get the total error, which called the sum of squared errors or SSE. This shows how well the model fits the data. The smaller the SSE, the better the fit.
now for the discussion, we're going to achieve three main points. So what we use is the assignment focuses on analyzing global temperature, which changes using the data from NASA. The selected data set includes the most recent 10 years, from 2015 to 2024, to highlight the noticeable rise in global temperature in the past decade. The purpose of the analysis was to develop a mathematical model that best fits the data and help explain the observed trend in temperature anomalies. There are types of curve fitting models we use, and the first one a linear, quadratic, and also exponential model. And we also integrated Python into the calculation too to ensure a more match the actual data. The comparison was then based on the sum of square errors (SSE), which it measures how far the model's predicted values are from the real data. So to conclude is SSE means when the smaller the data of SSE, the model fits the data better. So among the models tested, the quadratic least square, like I mentioned before, produced the lowest SSE, 0.0714, showing that it was following the pattern of the data more closely than the others. Therefore, this model was selected as the best representation of the trend. And next, our challenges during the analysis was the limited number of data points. Because we only use 10 years of data increases the chances of overfitting, especially with more complex models like quadratic and exponential forms. However, by comparing the SSE value carefully, the most appropriate model was chosen. Another challenge was deciding whether to use the no smoothing or lowest 5 version of the data provided by NASA. We ultimately choose the no smoothing column as it reflects the raw yearly variations more directly. So what I can conclude from this discussion is the result clearly shows an upward trend in temperature anomalies in recent years, which it confirms by ongoing issues of global warming. The model only not supports this trend but also provides a way to understand and predict possible future changes to improve future analysis. A longer time span of data could be included to check these are our recommendations lah. For the trend to remain consistent over a broader period. Additional variables such as greenhouse gas levels, deforestation rates, or ice sheet loss could also be added to gain a deeper understanding of the climate system lah. Even with some limitation, the assignment demonstrates how mathematical modeling can help explain real-world environmental changes in a clear and meaningful way. As for the conclusion, first of all, we have achieved all the objectives that we have stated just now. And this assignment has shown how curve fitting techniques can be used to model and understand global temperature changes. By using temperature anomaly data from last 10 years, different mathematical models were applied, and the best was fitted in this trend. The comparison of error values help identify the most accurate model for this dataset. The results show a clear increase in global temperature, which supports concern about climate change, even though the analysis uses a limited number of data points. Instead, provided useful insights. Overall, the assignment demonstrates a very usefulness in mathematical tools in analyzing real-world environment data and highlights the importance of continued monitoring and study of climate change.